Bismillahirrahmanirrahim. In today's lecture, we will discuss about the band structure and the relevant property to the band structure. This topic has been taken from the course outline of Nanophysics and Technology, having the course code of PHY445. Actually, material in the basis of electrical conductivity are divided into three types. One is called as a conductor, others are the insulator, and the third one are the semiconductors. If you see conductors, then the curve for the conductors for the resistivity versus temperature curve for the conductors is look like this one. This is shown in figure A. Here we see there is a limited resistivity at 0 Kelvin, but when we increase the temperature, there is gradual increase in the resistivity with increasing temperature. This is the behavior of normal conductors. There are some low temperature conductor in which the variation between the resistivity and the temperature is a bit different. It is shown in the figure B, but keep in mind again there is a limited resistivity even at 0K. So these are called as a conductor. We have semiconductors, and the behavior of semiconductor is a bit different. With increasing temperature, the resistivity of semiconductor decreases. With increasing temperature, the resistivity of semiconductor decreases, and while with the decreasing temperature, its resistivity increases. So this is some typical behavior of the semiconductor material. This is actually a data chart regarding the metal versus semiconductors. We have example of copper and germanium at different temperatures. At 0 degrees C, it has been shown that the resistance of copper is 31 ohm, while the same germanium has 5.2 ohm. Similarly, at 25 degrees centigrade, it is 33 for copper and 4.2 for germanium. In the case of 50 degrees centigrade, it is 37 for copper and 1.2 for germanium, and at 100 degrees centigrade, it is 44 ohm for copper and 0.029 ohm for germanium. If we see from the data chart, it is clear that with increasing temperature there is a gradual increase in the resistivity of copper, while in case of germanium the increasing temperature reduces the resistivity. So this is some typical behavior. In case of metals, when we increase the temperature, then the amplitude of vibration of the metals increases, of the lattice points or the atoms in the metals increases. So there is greater probability that the free electron that are responsible for current or for the transfer of charges, that will collide and its motion will be resisted. This is the actual reason why is resistivity increasing with increasing temperature, because increasing temperature increase the amplitude of vibration of the lattice point or the atoms inside the metals. In case of germanium or in case of semiconductor material, when we increase the temperature, so there are more possibility that electron from the conduction band from the valence band will move toward the conduction band due to high thermal energy, and that electron could be useful for transferring the charge or as a carrier for the current. So this is the actual way that increasing temperature increase the number of carrier in case of semiconductors, and that lead to the improvement in the current or reduction in the resistivity. So this is energy gap for a simple material. we have a valence band and conduction band. If we explain the semiconductor, conductor and insulator based on band theory of solid, then it is very simple. In case of conductor, there are two possibilities. Either the valence band or conduction band overlap each other, and the electron from the valence band can easily move toward the conduction band. The other possibility is that the difference or the energy gap is so small, so that even the thermal, the room temperature is enough to move the electron from the valence band toward the conduction band. So they are readily available for the current when external potential difference is applied on it. If we look toward the semiconductor, in case of the semiconductor, the difference is between the valence band and conduction band is a bit high. So even if we check this material, that at 0K there is the valence band is completely full and the conduction band is completely empty, so there is no current and it is perfect insulator at 0K semiconductor. But if we increase the temperature, and it is if a normal even at room temperature, so there is a possibility that some of the electron will move from the valence band toward the conduction band, that would be readily available for the transport of charge when an external potential difference is applied on it. And in case of insulator, the gap between valence and conduction band is so high, so that even the thermal energy or the room temperature is not able to shift the electron from the valence band toward the conduction band. So that are actually the perfect insulator and that resist, because there are no carrier. If you apply external potential difference on it, there will be no transport of charges. So this is actually the leap required for the electron from the valence band toward the conduction band, that is called as the band gap. So this is the simple case of conductors. The valence, the free electron can move easily inside the metal, but these are actually free in the sense that it can move inside the metal, but it cannot leave the metal. If we want that electron to move the metal, to leave the metal, we need to give a minimum required amount of energy, that is actually called as the work function of that metal. But anyhow, these electrons are actually randomly moving when no external potential difference is applied on it. When we apply an external potential difference on it, so these electrons are drifted in a particular direction, and that is why we can observe the current. So these electrons freely move among these orbitals within an energy band, as long as the orbitals are not completely occupied. So these are actually the band structure of conductors. If either the band gap is very slow, so that the electron can move from the valence band toward the conduction band. So here in the valence band is empty and the conduction band is full. So the electron, even the thermal energy, can bring the electron from the valence band toward the conduction band, and the electron can easily move in the conduction band when external potential difference is applied on it. Conductors have overlap permits of electron to freely drift between the bands, and that is because the energy gap is very small, or maybe in some cases the valence or conduction band overlap or each other. These are actually the insulator. The band gap between the valence band and conduction band is high enough, and even it's hard for the electron to move from the valence band toward the conduction band. The valence band is completely packed and the conduction band is completely empty. Here you can look to in the figure. So that is why there is no whole current inside the valence band, because it is completely packed. Even if you apply an external potential difference on it, there will be no motion of charges, because no charges are available in the conduction band, and the valence band is completely packed because the charges are bound to each other. So we have band theory of solid to explain this. That is actually explain the account of decreasing resistivity with increasing temperature, as well as other property of semiconductor from the band theory of solids. So this information we can get from allowed energy states for electron that are nearly continuous or certain range, in case of that particular energy band. even if we consider in valence band or conduction band, that are actually the allowed states, but in case of the band gap, that are the forbidden states. So this is the band theory of solid, we can see, and we can explain its potential with respect to this curve by drawing its potential against the distance between the lattice points. So band theory of solid describe the wave function associated with the electron, and from that we can get the how the electron can interact with the lattice point, and what is the behavior of the electron near the lattice point and in between the lattice point. So that is a type of periodic potential, and there are different theories provided about this periodic potential. We have free electron model, nearly free electron model, chronic pinning model, and at the end the band theory of solid was provided. We will go through it. Here in this slide, the concept of symmetric and anti-symmetric wave functions are provided. So an atom in the symmetric state has a non-zero probability of being halfway between the two atoms, while an atom in the anti-symmetric state has a zero probability of being at that location. So the band theory of solid some provide the symmetric case of binding energy is slightly stronger, resulting in a lower energy state. Thus there is a splitting of all possible energy levels, especially 1s, 2s, and so on. So when more atoms are added in real solid, there is a further splitting of energy levels. With a large number of atoms, these levels are split into nearly continuous energy bands, with each band consisting of a number of closely spaced energy levels. So as I told you that to discuss the behavior of electrons inside the metals, there are different theories provided, and the main theme of this theory was to develop or predict or even drive or do the mathematical calculation for the potential of the electron near the lattice point, or maybe near the atoms or ionic radii, and in between the atoms. So there is a concept of periodic potential. So chronic pinning model is also a model that provided an idea or an effective way to understand the energy gap in semiconductor is to model the interaction between the electron and the lattice point. So this is something done by the chronic and Penny to develop this particular model. So in this model, as I told you, there is a concept of periodic potential. So there is a high potential near the atoms, near the lattice point. When we go away from it, so the potential dropped abruptly. So there is a periodic potential, and that repeat itself after equal interval of time, because we have a crystalline solid. So there are regular repetition of that atoms. So there is a potential. The wave function associated with that electron is given as because the electrons are not free, their energies are less than the height or the potential of each of these potential, but the electron is essentially free in the gap. That is actually the gap is 0 to x into a is actually the lattice point where its wave function is. So its wave function will look like wave function is equal to a e ki power, that is actually exponential function, I kx plus b e ki power minus kx. So this is some tunneling effect, just like we have quantum mechanical tunneling. Even when the energy of the upcoming electron or upcoming particle is less than the barrier, so there is a possibility that the particle or the electron will tunnel through that. So in that region, that is actually the region was that is between a and a plus b, the electron can tunnel through the wave function, and the wave function loses oscillatory solution and become exponential. So this is for exponential case, we have wave function psi is equal to c e ki power kx plus d e ki power minus kx. So this is some solution of the chronic pinning model, where the matching solution at the boundary, the chronic pinning find that k square b divided by 2k sin k alpha a plus cos k a is equal to cos capital Ka. So here K is another wave, that is actually the wave number, and that is actually equal to 1 over lambda. So further explanation about the chronic Pini model is made in this equation. In this slide we see how this periodicity is found, and we have a forbidden or allowed energy region for it. As we discussed that actually in isolated atom we have energy levels that are discrete, but when we move towards the more atom, that is the molecules, so there are molecular orbital, and in the case of solids, the molecular orbital or the atomic discrete level are converted into bands, and there are allowed energy band and forbidden energy bands. So that is actually allowed energy range bands are the band where electron can move freely, where forbidden are the range range of the energy where the electron cannot reside over there. So here in this model is shown where is the forbidden or allowed energy range for the electrons. So the forbidden zone is mentioned with the white color, and the allowed range is shown with a particular color. So here we can see how the there is a periodicity on a particular K value. So we see that the electron can easily migrate between the allowed energy regions, leaving behind the forbidden energy range. So there are some difference between the chronic Pini model and single potential well model, but anyhow these all models are provided to explain the periodic behavior of the electrons inside the metals. So if we explain the conductivity and the band theory of solids and their ideas to explain the semiconductor, conductor and insulators, then we can say that the band theory is helpful to understand or to make a difference between the conductor, insulator, semiconductors. So conductors like copper that can be easily explained with the help of free electron models. I means the electron are randomly present there. When we apply an external potential difference on it, it can move or it can be drift in a particular direction. So it's also possible to make a conductor using a material with its highest band field, in which case no electron in that band can be considered free. So if this field band overlap with the next higher band, that is however, so that effectively there is no gap between these two bands, then an applied external potential difference or electric field can make an electron from the field band jump to the higher energy levels. So this is actually the behaviors of we call as a conduction to take place, although this is typically with slightly higher resistance than in normal metals. So such materials are known as semi-metals. So valence and conduction band are very important. The concept of valence and conduction band to understand the insulator, conductors and semiconductors. So both in insulator and semiconductor there is a field energy band that is called as a valence band, separated from the next higher band that is called as a conduction band by an energy gap. So if this gap is at least several electron volts, so this material is an insulator. It is too difficult for an applied field to overcome that large energy gap, and the thermal excitation lacks the energy to promote the sufficient number of electrons to the conduction band, and that is why if we apply an external potential difference on the insulator, there is no current over there. So there is smaller energy gap between the valence and conduction band in case of semiconductors. For energy gaps smaller than about 1 electron volt, it is possible for the electron to be excited thermally into the conduction band, so that an applied electric field can produce a modest current. So these are actually the semiconductors. So we have semiconductor theory, and in the semiconductor theory at 0K, the valence band is completely full and the conduction band is completely empty. So that is why there is no current 0K in case of semiconductor. So there is some relationship between the temperature and resistivity, as we discussed in the earlier slide. So when the temperature is increased from 0, so there are more atoms are possible to be excited. So an increased number of electrons in excited state explain the temperature dependence of resistivity and semiconductor. So it means actually there is a relationship between the temperature and resistivity of materials. And earlier slide, even I think in the first slide, we mentioned how there is variation between the conductor, insulator and semiconductors, between the temperature and resistivity of that particular material. So in case of intrinsic semiconductor, we have the concept of holes and electron, because there is no net charge on this intrinsic semiconductor. When an electron is moved from the valence band toward the conduction band, so it leaves behind a hole, that is actually a missing electron in the valence band. So we have two carrier in this case. One is the electron that is present in the conduction band, and other is the hole that is present in the valence band. So similarly, if we increase the temperature of this material, so there is more possibility that more electron will break the bond and move from valence band toward the conduction band, leaving behind holes. So there will be a current due to the electrons, that is called as electronic current, and in the opposite direction there will be current due to holes, that is due to the positive charges. So if we add some impurity in the semiconductor, so there are some charges. So based on the nature of that impurity, it might be p-type or n-type material. So maybe it's have a positive excess charge or negative excess charge, or maybe electron or hole, leaving behind an energy gap in creating an energy state even in the band gap that reduce the resistivity of that materials. So we have n type of materials. In case of n type of materials, some semiconductor material, just like some material just like arsenic or silicon, that is actually the n type semiconductor materials. The electron are close to the conduction band, that will eventually carry electrical. So in this case we have an electron that is actually a majority carrier in this case. So there is a donor level, because an electron there exists and easily donated by the conduction band. So we have acceptor level, that is at p type of materials, and that both the level, donor level or acceptor levels, are created in the band gap, and that leads to the band gap energy, that lead to the reduction in the band gap energy, and allow the even the low energy to move the electron from the valence band toward the conduction band, and that lead to the improvement in the electrical conductivity of such material. So this is something about the conductor, insulator and semiconductor and the band theory of solid. So in next class we will discuss the relationship between the bands, structure of the material and the optical properties of semiconductor material. Thank you very much.